Hi, this is Vivek,
Hello, this is Swaraj.
and we are working on the project Surgical Skill Prediction with Instrument Segmentation. So, as we all know, that surgical skills are very important for a patient's safety and well-being during a surgery. And traditional assessment of surgical skills was done using manual efforts, which was inefficient and lacks repeatability. So, this model is going to automatically predict surgical skill using a surgical video. So the model considers three important aspects of surgery, which are helpful in categorizing, which are helpful in getting the surgical skill for that particular surgery. And these three aspects are surgical tool usage, surgical field clearness, and surgical event pattern. And as we can see on the image in the slide, that a sharp and smooth tool movement indicates a good surgery, whereas a jerky movement with large dissection area indicates poor surgery. Similarly, higher visibility of anatomy structures, which is important for a surgeon's performance, is seen here. Whereas uh, obscure field, which could have been caused due to burnt tissue or excessive bleeding while the surgery, indicates that a surgery has not been performed well. And a linear sequence of events indicates that the optimal procedure has been formed at a good surgery. It was a good surgery. Whereas if there is repeatability of steps involved, it indicates that there's poor skill. So coming to the literature review, the previous works in this area have focused on one of the three skills: tool, event, or proxy. And our framework, on the other hand, unifies all these skills to give a single score based on individual contributions from these skills, as well as a dependency of them on each other. So coming to the model architecture is such that we have four parallel paths with similar architectures, and each path focuses on one skill aspect: tool, event, proxy, and there's a fourth visual path, which is a baseline path, which learns directly from the visual semantic features from pre-trained neural networks. And each path has an input, which is a feature sequence which contains features specific to that skill aspect. And so after getting the input, we are encoding it using an encoding function to get an embedding. And finally, we calculate a score from that encoded input using a scoring function. And this score is specific to that path. But as we spoke earlier also, that there is an interdependency of these skill aspects on each other for calculating the overall score. So we also calculate a importance weight of each path. And this is basically the score that we calculated for each path. And then we calculate an importance weight for each path. And we finally calculate an overall score by averaging the scores of each path weighted by their importance weights. And this is also done for each time step, averaged over each time step, since this is a temporal dependence. And coming to the loss functions, we have a supervised mean square error loss. But since this is a medical task, there is scarcity of annotated data. So we also need a self-supervised contrastive loss, where basically a prediction function is used to forecast the embedding of the future based on recent past. And it tries to make the future embedding similar to the embedding on that time step and different from all other time steps. So this model was tested on two data sets: the clinical data set created by the authors of this paper, and a Jigsaw's data set, which is a simulated data set, and it achieved state-of-art results on various parameters. So now we'll move on to the unsupervised instrument segmentation.
So I'm going to be talking about an unsupervised instrument segmentation model. So the most of the previous efforts have been supervised segmentation methods, which require laborious and expensive human effort. So this is an unsupervised method, which takes into account cues, and these cues are used as pseudo labels for instruments and background tissues respectively. So this is the framework. So as I said, there are three cues being used here, and these cues are they make the anchors, and these anchors are what is called the pseudo label. So we have three cues. The first one is the color, the second one is the objectness, and third is the location. So I'll explain color. If in a video, when we have the instrument is mostly grayish or plain in color, while the background tissues are reddish. So using that, a probability map is generated, which detects the probability of an instrument being there at a certain pixel. This is done for various other cues like objectness and location as well. So the anchor generation. So using these cues, an element-wise product is taken, and there are two types of anchors being generated, positive and negative. So in a positive anchor, we know if the pixel is 1, we know for sure that the instrument is present at that pixel. So two anchors are generated, the negative anchor being the probability of the background being there, and the positive anchor being the probability of the instrument being there. So these are the pseudo labels that we'll use for training our models. So the anchor loss, this is the loss that we need to minimize. This After generating the positive and negative anchors, we calculate the loss, the anchor loss, and we train our model based on this loss. So apart from the anchor loss, we also have a semantic diffusion loss. So apart from these handcrafted cues that we are generating, we also have, we need another source of labels. So we are using the temporal coherence of the frames. So images of adjacent terms usually share semantics. So this is called the interframe instrument-instrument similarity. So using this, we are calculating a semantic diffusion loss between two adjacent frames, and this is done for both in interframe instrument similarity and interframe background similarity. So we are checking the semantic loss between two frames, and lastly we add all of these losses, and this is the total loss that we need to optimize. We need to minimize this basically. So based on this model, we have certain results. We tried a combination of cues, and we are using two metrics here, the intersection over union and dice, and we're getting the best values for when we are using all the three cues together, as you can see here.
Yeah, we tried out a few experiments on the Jigsaw's dataset for the skill prediction, and there are 3 tasks in the Jigsaw's dataset: knot tying, suturing, and needle passing. And we have gotten results train MSC and test MSC, as well as the Spearman rank correlation coefficient for knot tying as well as needle passing. And as the subsequent work, we would be generating cues. Basically, till now we were using the kinematic data from the Jigsaw's dataset to calculate skill prediction. Now we will be using the unsupervised segmentation method that Swaraj mentioned, and we would modify the cues a bit so that they work on the similitude data set, because they were for now they were designed for the clinical data set, and we would then compare the skill score with the unsupervised tool segmentation against the kinematic data from Jigsaw's data set. Thank you.